You've probably heard that we're living in a plastic age. And that's not wrong. But it's actually bigger than that. We're living in a polymer age. These amazing materials are in pretty much everything you touch. And today, we're going to pull back the curtain and see the simple molecular secrets that make it all possible.
Think about it. It all starts with something as simple as the plastic bottle you're drinking water from, or the synthetic rubber in the tires on your car that gets you from A to B.
And yeah, even the polyester and nylon fibers that are woven into the clothes you're probably wearing right now.
So, what's the invisible thread that ties all of these incredibly different things together? Well, the answer is simple, but it's also incredibly powerful. They are all polymers.
So here's our game plan. We're going to start with what a polymer even is. Then we'll look at how these tiny molecules link up to build massive chains, and, this is the cool part, how the shape of those chains gives a material its properties. And that shape is what decides if a plastic can be recycled or if it's permanent, and finally, we'll wrap it all up with why this stuff really matters.
Okay, let's dive right in. What exactly is a polymer? I mean, to really get a handle on the plastic age, we've got to understand the word that started it all. The name itself actually gives us a huge clue. It comes from Greek, poly means many, and meris means parts. So a polymer is really just a giant molecule, a macromolecule, that's made up of many, many repeating parts, all linked together in a super long chain.
And what are those repeating parts called? They're called monomers. It's simple, right? If the polymer is the whole chain, a monomer is just a single link. It's the basic building block used over and over and over again. Let's make this super concrete. Take a look at this. This is ethene, a really simple monomer. Now, when you get thousands of these little guys to link up in a chain, they become polyethene, literally many ethenes. And just like that, you've made one of the most common plastics in the world, the stuff in plastic bags and squeeze bottles.
So, we know about the building blocks, but how do they actually connect? Let's take a look at the blueprint, the different ways chemists actually build these incredible molecular chains.
Right, we've got our monomers, our little individual links. But how in the world do you get them to form a chain? Well, it turns out there are two main ways to get the job done.
The two big methods are called addition and condensation polymerization. With addition, it's pretty much what it sounds like. You just add monomers to the chain, one after another. Nothing gets lost. The final polymer is just the perfect sum of all its parts. Now, condensation is a little different. To make a bond, two monomers have to kick out a tiny molecule, usually water. So the key difference to remember, addition is a clean merge, but with condensation, you lose a little something to make the connection stick.
Okay, but just building the chains isn't the whole story, not even close. The way those chains are arranged, what we call their molecular architecture, is what gives a plastic its final unique personality. And this is where it gets really fascinating.
First up, you can have linear chains. The absolute best way to picture this is to think of a big bowl of cooked spaghetti. Each strand is a long, individual polymer chain. Sure, they're all tangled up, but they can still slide past each other, and that's what makes the material flexible.
Next up, we've got branched chains. Let's stick with our spaghetti, okay? Imagine some of your spaghetti strands now have little side strands branching off of them. These branches kind of get in the way, right? They keep the main chains from packing in super tight, and that usually makes for a less dense material.
And finally, the third type, cross-linked chains. Now imagine you take that whole bowl of spaghetti and you pour superglue all over it. The strands aren't just tangled anymore. They are chemically bonded, fused to each other. They've formed this one single massive rigid net. They can't slide around at all. And this simple picture is going to lead us directly to the two major families of plastics, the ones we can recycle and the ones that are, well, permanent. And that whole molecular architecture thing we just talked about, that's the reason for this huge difference.
So here's a question for you. Have you ever wondered why you can melt down a plastic water bottle and turn it into something new, but if you try to do that to the hard plastic handle on a frying pan, it just burns and smells awful? The answer is all in those chain structures.
And this chart breaks it all down beautifully. On the left, we've got thermoplastics. These are our spaghetti strands, those linear or branch chains. When you heat them up, the weak forces holding the chains together break, letting them slide around. They get soft, they melt, and you can reshape them. That's why they're recyclable. But on the right, you have thermosetting resins. This is our superglued network. The chains here are locked together by super strong covalent bonds. Think of them like chemical welds. When you heat these, those bonds don't break. The whole thing just chars and falls apart. They are set in their shape permanently, and that's why you can't recycle them.
And you know these plastics from everyday life. Your recyclables, the polyethylene in bottles, PVC pipes, polystyrene cups, they're all thermoplastics. The permanent, non-recyclable ones are things like Bakelite, which was used for old phones and light switches, or the super strong epoxy glues you might have at home. You just can't melt and reuse them, all because of that rigid, cross-linked structure.
So, let's zoom out for a second and connect all these dots. We've seen this amazing journey from a simple little molecule all the way to the huge world of materials that we use every single day.
So the crucial takeaway is really this simple, logical flow. It all starts with the monomer. Then, how you link them, addition or condensation, builds the chain. The shape those chains take, linear or cross-linked, decides how the material behaves. And that is what ultimately tells us if we have a recyclable thermoplastic or a permanent thermoset. It's this incredible cause and effect where tiny, tiny changes at the molecular level create the massive world of plastics we see all around us.
And that leaves us with a final and pretty critical question. Our world is built from polymers. Now that we understand the molecular blueprint, the challenge for us is clear. How are we going to design the next generation of materials to be both high performance